Hey everyone, and welcome. Today, we are going to get right to the heart of, well, everything. We're talking about the fundamental forces that build the world around us. Chemical bonds. This is the invisible glue holding it all together. So, let's dive in.
I mean, have you ever really stopped to think about that? Seriously. Right now, you are surrounded by just an unimaginable number of atoms. So what's stopping them from all just, poof, drifting apart? What's holding you together? Or the chair you're sitting on? Or even the air you're breathing?
Well, the answer is this amazing, super powerful force. It's what allows atoms to link up and for molecules, crystals, you name it, all the stuff that makes up our reality. You can really think of it as the ultimate cosmic glue.
Okay, so what's the deal here? What's the motivation? I mean, why do atoms even bother connecting with each other? Well, it turns out they're all after the exact same thing.
You know what it is? It's all about stability. See, atoms are kind of like us. They're happiest, or let's say most stable, when their outermost electron shell is completely full. They're trying to be like the cool kids of the periodic table, the noble gases way over on the right. Those guys are super stable. And believe me, other atoms will do pretty much whatever it takes to get that same setup.
So, to get that stability, atoms use their outermost electrons. We call them valence electrons. And they're basically the currency of bonding. It's a transaction. They can give them away, they can snatch them up, or they can decide to share them. And how they handle that electron currency, well, that defines everything about the bond they form and the kind of stuff they end up creating. All right, so let's check out our first type of transaction. This one is a pretty straightforward case of give and take. We're talking about ionic bonds.
So, an ionic bond is what happens when one atom just completely gives its valence electrons to another one. This isn't about sharing, not at all. It's a total transfer. And when that happens, you get ions. The atom that lost an electron becomes positively charged, and the one that snagged it becomes negatively charged. This is the classic story of a metal, which is usually happy to give away electrons, meeting up with a nonmetal, which is really eager to take them.
So, what's the driving force behind this whole transfer? It comes down to a property called electronegativity. Honestly, the best way to think about it is an atom's greed for electrons. So when you have one atom that's kind of loosely holding onto its electrons, and it gets near an atom with a super strong pull, well, it's no contest. The greedier atom just rips that electron right away. And what happens next is actually pretty fascinating. Now you have these positive sodium ions and negative chloride ions, and opposites attract, right? They are powerfully drawn to each other, like a bunch of tiny little magnets, and they snap together into this really beautiful repeating pattern called a crystal lattice. This super strong attraction is why table salt is a hard solid that you have to get really, really hot to melt. But it's also why it's brittle. Think about it. If you smack a salt crystal, you can knock those layers out of alignment. All of a sudden, you've got positive next to positive and negative next to negative. They repel each other instantly, and the whole thing shatters. Okay, so that's what happens when one atom bullies another. But what happens when atoms decide to cooperate instead of compete? Let's move on to our next bond type and see what kind of completely different materials we get. You know, way back in 1916, the brilliant chemist Gilbert N. Lewis just nailed the idea behind our next bond type. He said an electron can be part of the shell of two different atoms, and you can't really say it belongs to either one. It's not about a transfer anymore. It's all about sharing.
And that right there is the covalent bond. This is what happens when two atoms have a pretty similar greed for electrons. Neither one is strong enough to just rip an electron away from the other. It's like a tug of war where nobody wins. So what do? They compromise. They agree to share electron pairs, and that way both atoms get to feel like they have a full, stable outer shell. And this is a huge deal. This is the bond that holds together pretty much all the molecules of life. We're talking water, the food we eat, even the DNA in every single one of your cells.
And the really cool part is that we have a super simple but really powerful way to draw this all out. It's called a Lewis structure. Think of it like a little blueprint for the molecule. And drawing one is actually kind of like solving a fun little puzzle. First step, you just count up all the valence electrons you have to work with. Then you pick a central atom to be the core. After that, you connect all the other atoms with single bonds. And for the final step, you take whatever electrons are left over and sprinkle them around to make sure every single atom is happy with the full outer shell. Simple as that. And here's the key takeaway. This simple act of sharing just one pair of electrons can create some of the most important molecules out there. Take methane, for example. That's the main stuff in natural gas. You've got a carbon atom sharing one pair of electrons with each of 4 hydrogen atoms. Boom. 4 strong, stable single bonds.
But what happens if sharing just one pair isn't enough to make everybody happy and stable? Well, no problem. Atoms can share more. In this molecule here, the 2 carbon atoms are actually sharing 2 pairs of electrons with each other. We call that a double bond, and as you might guess, it's stronger and a little shorter than a single bond.
And why stop there? We can take it even one step further. The nitrogen gas that makes up, like 80% of the air we're breathing right now? That's held together by a triple bond. 2 nitrogen atoms sharing 3 pairs of electrons. This thing is one of the strongest covalent bonds out there, which is why nitrogen gas is so incredibly stable and doesn't like to react with much. All right, time to dive into our last major type of bond. And this one is what explains all the cool and unique properties of metals. You know, the stuff we build just about everything with.
We call this metallic bonding, and the absolute best way to picture it is with something called the electron C model. So imagine this. In a chunk of metal, all the atoms basically give up their valence electrons to a big community pool. So what you end up with is a grid of positive metal ions just kind of floating in a sea of electrons that flow all around them. These electrons don't belong to any one atom anymore. They're delocalized. It's just a fancy word that means they're free to roam around the entire piece of metal.
And this electron sea idea? It just perfectly explains all the classic properties of metals. Why are they shiny? Well, that sea of electrons acts like a mirror and reflects light. Simple. Why do they conduct heat and electricity so well? Because those free-flowing electrons can easily zip through the material, carrying energy along with them. And why can you bend them? Why are they malleable? It's because the metal ions can literally slide past one another in that electron sea without breaking the whole thing apart.
Yeah, just think back to that brutal salt crystal for a second. If you hit it, it shatters into a million pieces. But when you whack a piece of metal, the positive ions just slide to a new spot within that super flexible electron sea. The bond holds, the material just changes shape. That is the magic of what we call malleability. Okay, let's bring this all home. We've looked at 3 totally different ways that atoms can use that currency of electrons. We've got transferring, sharing, and pooling. So now let's put it all together and see how this invisible glue really does build the entire world around us.
So here it is, the big takeaway. It really all boils down to how atoms handle their electrons. Are they transferred, are they shared, or are they all pooled together in a sea? That single decision dictates the properties of everything we see and touch. Ionic transfers give us brittle things like salt crystals. Covalent sharing gives us this incredible range, from diamond, the hardest stuff we know, all the way to soft things like wax. And that metallic sea of electrons, that's what gives us our strong, bendable metals.
So to wrap this all up, these 3 major bonds we talked about, ionic, covalent, and metallic, these are the intramolecular forces. That's the glue inside molecules and crystals holding the atoms themselves together. They answer that big question we started with, why doesn't the world just fall apart? But that leads to another really interesting question, doesn't it? What about the forces between different molecules? You know, the weaker glue that makes a bunch of water molecules stick together to become a drop of water. Well, that's a whole other story.